Okay guys, so can we get started please? Okay. Just a very brief recap of conjugate beam method. I think so towards the end we a bit fast-tracked the sign convention and everything, so I just wanted to tell you, like, you know, how would you adopt the sign convention. Okay. In the conjugate beam method, as I told you, conjugate beam method means that you have a virtual beam or an unreal beam, a fictitious beam, which is subject to bending moments, the actual bending moment of a structure. Okay, so the real bending moments, you apply that on a beam. Okay, that assembly is called a conjugate beam. Now, in that, if you are asked to find out rotation or the deflections at a particular point, you have to do nothing more than finding shear, which will be analogous to the slope, and moments, which will be analogous to the deflections. Okay, so that's all you need to do. So, for example, if we did this problem in the previous class, where we were interested in finding out our deflection at point B. So we drew its moment diagram by parts, just placed it on the beam, and then after that we worked out the shear and moment at this location, okay, at point B, which happens to be 1 meter from the support point A. Now, what happens is that please make sure that if our bending moment is negative, yeah, I place the points, the load is applied facing down. Yeah, if it is positive, the load is applied facing up. Yes, and what did we get in the end? So, if we find out the reaction, if we are interested in finding out the reaction, how can we, the shear at point B, what should we do? First of all, we find out our reaction. And from the previous analysis, what was our reaction? Can anyone help me out? What was that?
Minus 400 over 3 EI.
And it was facing down. Minus 400 over 3 EI. That was our reaction. Okay? Now, in order to find out the moment at B, we have to multiply this reaction with 1. Yes, so that comes out to be minus 400 by 3 EI times 1 plus. Why? Because we have this portion of the bending moment which is facing up, plus. Why plus? Because this is coming out from the plus moment, okay? And so, and this was 100. This was 100, wasn't it? Based on similarity. So, you take half into 100 into 1 by 3.
Yes, sir.
That's what we, and in the end, what did we get? Minus. What was that? Please give me the answer.
Minus 116.67 over EI.
Minus 116.67 over EI. Now, this is coming out to be negative. Okay? What does this negative mean? This negative means that the deflection is downward. In other words, deflection is in the direction of this force, which is due to the negative moment. Okay, so the deflection is negative because it is in the direction of this one. Okay, this thing you have to make sure. Similarly, if you are trying to find out your shear, you can do the same thing. Okay, so please, I will invite you to go through the examples of Hibbler book. This is structure analysis, the one which I am using, R.C. Hibbler, 6th edition. Okay, and just do the examples, and I think so your concept will become further clear. Okay, so that's what he is also doing. But take the PDF which I sent you. That has got like a detail. Hibbler doesn't do the details. He gives lots of problems. Okay, so the mechanics behind it, you will find it in the PDF which I sent you. Okay, so that thing you have to make sure. Okay, any question about conjugate beam method? Shall we move forward? So we'll now start with the new method, which is called virtual force method. Let me rub this conjugate beam method off. Okay, I'll just. Virtual force method. Guys, it is very important that you understand the basic philosophy behind any method. And you know what? The name gives you a lot. Okay, it tells you a lot. It tells you what's the mechanics behind it. In the conjugate beam method, I told you conjugate beam method is not real. Conjugate is something unreal. And why? Because the whole method was encapsulated by an unrealistic, by a bending moment diagram, which in reality is not applied, but you treat that as a load. So therefore, the name was coined as conjugate beam method. Now, this is called virtual force method or virtual work method. Okay, virtual work method has got two types. One is virtual displacement, another one is virtual force. In your course, you are doing virtual force method. Virtual displacement method is also similar. But we'll be discussing over here virtual force method. Now, what is virtual? Virtual means which is again not real. Okay, so in this analysis also, we are making use of something which is not real. We are using that tool to find out our deflection. Okay, so that is important for you to understand. Okay, virtual force, so the first thing which should click in your mind is that there is something again fictitious going on, and that will be used to aid your working out of your deflections. Okay, now this statement which I have written, this is very important. One thing you must appreciate, out of all the methods which we have done so far, if the most important ones are the virtual force, the virtual work methods, okay, and the conjugate beam method. So these work methods, they are the most important ones. Why? If you are thinking of doing advanced structure analysis, this is the basics of it. This is the foundation. Okay? All your computer analysis, whatever you do in the softwares, everything is based on virtual work method. So understanding of this method is very important. Okay, like moment area methods, conjugate beam methods, they are good, but they become very tedious if your number of supports increases, if you go to undeterminate structures. These sort of methods, they are very simple and they are very easy to be incorporated in computer analysis. Okay, so that's why these methods are used. So if you do advanced structure analysis or advanced finite element analysis, that is based on this one. All your nonlinear analysis, structure analysis, everything is based on virtual work method. You will see the shine of virtual work method glimmering everywhere. Okay, in structure analysis. So even in soil mechanics, in fluid mechanics, these have got the role. So this is a very important technique, and that's why I wrote this statement so that we can understand what we are talking about. Okay, and if I write anything, it is important that you understand every word of it. Okay, what is the mechanics behind it, and that thing must be clear to you. So let us read it out and see whether we understand it or not. Okay, shall we? Yes? Okay, principle of virtual forces. Suppose that a beam or a frame is in a displaced configuration. A beam or a frame is in a displaced configuration. Means I've got a beam and I displace it like this. Okay? So we have got a beam or a frame which is displaced. So let us draw a beam which is, so let's assume that we have got a beam, a simple beam, and which is subject to some loading, and it is displaced. Okay? Yes? So a beam or a frame is in a displaced configuration. Now please focus. In which the actual displacement, V of x, actual displacement, so he's talking about the elastic curve, the equation of the elastic curve. In double integration method, we did the elastic curve, we derived the whole equation of the elastic curve. So V of x is the equation of this curve. Okay, actual. This is very important, guys. Let me underline it. Actual, in which the actual, this actual is because virtual work method, you will always be dealing with virtual and actual. We are talking about the actual structure which is given to you. So this is the actual structure and this is the actual displacement V of x. Okay, so let's call it a displacement V of x. Is compatible with the curvature distribution. Now what does that mean? Compatible with the curvature distribution. Can anyone tell me what does that mean? What is compatible with the curvature distribution? First of all, what is curvature? Curvature is, imagine, you remember we did 1 by rho is equal to K curvature, yes, is equal to d2y by dx square, yes, and or we can say d2 v of x by dx square. According to this one, it's d2 v of x, yes. So what does compatible means? Compatible means that in your elastic curve, what does d2y by dx square mean? This means that it is the change of, this is the, imagine I've got 2 points. One is this one and one is this one. Yes? And I draw tangent to them. Yeah? The rate of change of, or the angle between the two tangents, that is d2y by dx square, isn't it? Do you agree with me? dy by dx is the slope. Yeah? Yes? And this is the slope of a slope. So this is the, you draw the tangent and this is the tangent of the tangent. Do you agree with me on that? So, if this curvature is equal to d2y by dx square, then it is called compatible curve. When can you have incompatible curve? When can we have incompatible curve? Can anyone tell me? When? So when can that be? No, it's not. When the beam is, sorry? No, if it is, it's a displaced configuration. Okay? So, in a displaced configuration, when can we have the curvature not equal to d2y by dx square? We can have it when the beam breaks. If the beam breaks, if it cracks, okay, so your curvature, what happens? d2y by dx square, when you take the two change, the change between the tangents, that you can't take. Why? Because, why can't you take that? Why? Because one portion of a curve, imagine, is like this and another one is like this. So at this point, how will I take dy by dx and these are not connected with one another? So I can't take d2y by dx square. So that is what's called the compatible. Okay? Vx is compatible. So he doesn't want the be to an extent that the beam breaks. We are not talking about the failure. Okay? It is in a displaced configuration and the curvature must be equal to this one. In other words, it should be a continuous curve. Okay? It should be a continuous curve. The continuous curve, what is a continuous curve? If I draw a curve like this, yeah? I draw a curve like this. At every point I would have dy by dx, dy by dx, dy by dx, yes? dy by dx, dy by dx, but the moment I come over here, I will have one dy by dx and very infinitesimally close to that, I will have another dy by dx. Or at the same, so that is broken. Broken doesn't mean that it is moved apart. Maybe it's at the same position, but it is broken. Okay, so the dy by dx for this one is incompatible with dy by dx for the other point. Okay, so that is not a continuous curve. Okay, that's a broken curve. So it is incompatible. So we are talking about a curve which is compatible. Do you agree with me? Yes? So Vx is compatible with the curvature distribution. And we are talking about, remember, actual. And satisfies the kinematic boundary condition. Now what is a kinematic boundary condition? What are the kinematic boundary conditions? Huh? Slope, yes. Slope and deflections. Boundary conditions. If I am taking a simply supported beam, so the deflection at the ends must be equal to 0. That is the kinematic boundary condition. Okay? The slope should not be 0. That is a kinematic boundary condition. If it's a cantilever beam, yeah, if it's a cantilever beam, then the slope at the cantilever end must be equal to 0. The deflection at cantilever end must be equal to 0. So that is a kinematic boundary condition. Okay, so we have got an actual beam which is in a displaced configuration and whose actual displacement is compatible with the curvature, okay, and kinematic boundary conditions are satisfied. So does this curve meet this criteria? Yes. So this curve meets this criteria. Now we can apply the virtual work method on this, okay? Yeah. Now this is for the actual system. Then now from here the virtual system starts. Then any virtual load, now this is a virtual load, this is not a real load. Any virtual load Qx which is in equilibrium with a virtual bending moment. In other words, I take another beam, imagine I take another beam and subject it to a UDL. Yeah? So this I call, for example, a QX, Q bar X. Okay? So this is a Q bar. Why? Because now this is a virtual beam. Q bar is a virtual beam. So I take Q bar X and which is in equilibrium with a virtual bending moment distribution M bar X, and Q bar X must be in equilibrium with M bar X. What does that mean? What do we mean by Q bar X being in equilibrium with M bar X? So that means that you should be able to draw a proper bending moment diagram. This bending moment diagram is a UDL. This is a bending moment diagram for this, isn't it? That bending moment diagram is drawn based on equilibrium, isn't it? So in a virtual, so this is a real system. This is a virtual system. In real system, we have the elastic curve. and that elastic curve is the deflection, sorry, the curvature is compatible with V of x, the displaced profile. Yeah, that is the, so we are dealing with the elastic curve, with the geometry of the real system, the actual system, and we are dealing with the equilibrium of the virtual system. So he is saying that any virtual load which is in equilibrium with a virtual bending moment. So this is the virtual bending moment, okay? M bar x, okay? This bending moment profile is a virtual bending moment distribution and which satisfies the static boundary conditions. What are the static boundary conditions? What are the static boundary conditions? Sorry? Yes, moment and force. So moment at this point must be equal to 0 and there must be a reaction at this point. That is a static boundary. Yeah? At the fixed cantilever end, you should have moment, finite moment and a finite reaction. Yeah, so that is a static boundary condition. Okay? So in the virtual system, we have to ensure that there is a static boundary condition. Okay, so there is some virtual load applied and it is subject to and we have got m bar x. Okay, which satisfies the static boundary and makes the external virtual work equal to, so if these two are satisfied, if you have these two criteria satisfied, okay, then you can apply the virtual work method on it. And what is a virtual work method? Look at this. What is this? Virtual load. You can multiply the virtual load with the actual load. So this is actually the external work done, isn't it? Yes, external work is force times distance. But please notice, this is virtual load multiplied by the actual displacement. That's why it's a virtual work. It's not a real work. Why? Because we are taking virtual load. This is just from out of the blue. We are taking any beam. This can be of any support condition. This can be of any length, any beam you have taken. It's not necessarily the same beam, but you can equate that with this, with the actual beam using virtual work method. Okay, so this is a very powerful method. Okay, this can be any beam, as I said. It can be any support condition, any length, anything. Okay, and you can take these two. So look, you have the virtual load, external work. Okay, virtual load times the displaced profile. Okay, this displaced profile you multiply with qx, you get the external work, isn't it? And what is the internal work? External work is equal to internal work. Internal work is moment times curvature. M times theta is your work, isn't it? If someone asks you, how would you find out the work done by moment? So how can you do that? Moment times theta. And that theta is actually the curvature, isn't it? M times theta is, so any moment over here, any moment at this point, m bar x is equal to the relative angle between the two tangents, m times theta, like force times displacement. You have done, isn't it? Force times displacement is the work by force. M times theta is the work by moment, isn't it? You have done it in engineering mechanics. Agreed? Are you with me?
Yes, sir.
So you take moment and you multiply it with the curvature. Now, so how do you get this equation? How do we get this equation? It is very straightforward. We know that curvature kappa is equal to okay? Agreed?
Yes, sir.
I can put negative over here. Why? Why can I put negative over here? Sorry? Curvature is? Look, when your dv by dx, as you move in the direction of x, is it increasing or decreasing? It's decreasing. Okay, so dv by dx is decreasing as you move in x direction. So that's why I can put negative over here. Isn't it? Do you understand my point?
Yes, sir. Yes, sir.
Yeah?
Can you repeat it, please?
Sorry, I'm saying that your tangents, as your x is increasing, the tangent inclination is reducing until you reach to the one point where you have got 0. So with the increase in x, the tangent dy by dx is reducing. Okay, so therefore normally you put positive when your x is increasing and your numerator is also increasing. Both are increasing. But in this case your dy by dx is reducing as your x is changing. So no, we are talking about this one. Yes, so 0. But after 0, what will happen? It will start increasing. Then what? So, but the direction changes. You have got this direction, okay? The direction in that changes. So that's why it's again negative. Okay? So I'm talking about dy by dx. Okay? So dy by dx direction changes as you move up. So, okay. So this is kappa is equal to minus d2v by dx squared. Okay? That is your curvature. Now, you can multiply both sides with m of x, a virtual.
You are driving the formula.
I'm just giving you a hint. I won't derive it completely, but I'm telling you where is it coming from. Okay? So minus d2 v by dx squared into m bar x. Okay? Yes? Now, I can what is this equal to? Kappa?
d2 by dt.
No, this is d2y by dx square. Okay? Or let it be like this. Okay, let's not. Okay, so this is the right hand side, and this one, what happens? This one you have to do integration by parts. Okay, you do integration first function, integral of second, minus whole integral, differential of first, and integral of second, isn't it? So you do the integration by parts on this one, and what else? You put the boundary condition in it. you put the boundary condition in it and you get the right hand side, which is this one. Okay, so that's how you get your what is called the right hand side. But please remember that your moment over here, we have got moment. Yes, this moment is related to load, isn't it?
Yes, sir.
Moment is related to load, isn't it? How?
Moment is function of force.
Yes, but there. Remember, I wrote the relationship
Yes.
between the moment and the load. What was that? Load is equal to. Look, we have load, which is Q of x. What is it equal to? dV by dx, and dV and m is equal to B is equal to so this dV we can put over here and we can get d2m by dx squared. So that also you can put over here. That's why you get it in terms of q bar x. Do you understand my point? Sorry? You can't okay, no, what I'm saying is that you have got q bar x. Yes? Can you see this one? M bar x is equal to m bar x kx is equal to d2p by dx square. M bar x. Can you see that? So what I'm saying is that kappa is equal to minus d2p by dx square. Yes? You take a virtual moment, multiply it on both sides. Yes, multiply it like this. Then you can take integral of both these sides. Yes, this one is this one.
Yes.
Agreed? This is actually integration by parts. Yes, this is integration by parts. But you see, we have q bar x and b of x. So how do you get q bar x from m? How do we get q bar x from m? How is your moment related to? Moment is related to the applied load, isn't it? How is that? How is your moment related to the applied load? Look, we have load q of x is equal to dv d shear by dx. Agree? And shear is equal to dm by dx. So your qx is equal to d2m by dx square. So you can put that also over here. Do you understand? What do you mean double integral? There is not. It's not double integral. We are talking about only one x, one variable, which is in the x direction. It's not double integral. It's a product rule. First function integral of second. Okay, so because there are two functions of x, isn't it? If you have cos x times sin x within one integrals, so what do? You apply the multiplication rule, isn't it? So that's what you have to do over here and put the boundary condition. You will get this. Okay, I'm not going to go and derive that for you, but I'm saying that that's how it has got logic. That's how you work it out. Okay? Should I wrap it up?
Yes, sir.
Stop. I give you 5 minutes break.